So thanks again for joining this session, and we are going to spend a bit of time talking about testing, and the topic is now testing at the edges using mocks. And by that I really mean testing at the edges between the software and the real world, and between different software modules, and how can we do testing really at these kind of interfaces, because this tend to get a bit more tricky than testing something that's purely functional, as we will see in a bit. So first, let's see, I need to change back to PowerPoint. There we go. A brief introduction to myself for those of you who doesn't know me. My name is Anton Sundqvist, and I live here on the Finnish West Coast, where I have a small consultancy business doing typical ML system integration type of work. Lab doing a lot of tests and have some badges, and for those of you who have seen me present before, it's probably been on the similar topics around test-driven development, and I'm also for those of you, or if anyone have worked with me, you know that I'm kind of enthusiastic about test driving any code that I write, and I've also worked a lot on the tooling. Especially then LUnit and LMock, which is not the topic of today. So LUnit is the unit testing framework I released a few years back. I think it was the first GLA summit I introduced that one. And then LMock is the topic of this presentation, which is then a mocking framework. They get a lot of inspiration from JMock, which is a Java tool. So I'm going to talk about, we're going to have an introduction to unit testing, test-driven development, and to mocks and testables. I'm going to just explain the concepts so that we are on the same page, because then we're going to look at how we can use mocks to write tests and how they can help us. We're also going to look at how the LMock toolkit works, how that is used, how you can use it to script the boilerplate code generation, and what the API looks like, because it's a big part of the toolkit is the API and the expressiveness of it. So that's what I'm about to talk about. And as I mentioned, test-driven development is a development style that, at least for me, fits very well. It's it's essentially means that before you write any production code, you always write a test for what you're about to implement. So you kind of specify what you are about to write in code. And of course, this test will not fail because we haven't written the code yet, which is going to make it pass. So by just running the test, you then see that we actually test something useful, because the test is read, it fails. After that, we make the test pass, and this can be pretty quick and dirty. We just want to make sure that we understand what we are doing, and that we know where to make changes and so on. So it's more for guiding than what we're about to do. And then finally, you can go back, refactor, clean up, and tidy up the mess we might have made. So you tend to talk about this kind of red-green refactor cycle. So you have the red failing test phase, and then you make it green, make it pass, and after that you refactor, clean up. And importantly here is that the cycle time here is typically on the order of minutes if it's done well. So you have a very fast cycle. You write a small test which is just guiding you, guiding the development, pushing you in a direction towards a working system, and you make it pass quickly, then you refactor, and then you iterate, and you tend to write hundreds of tests. Is not a lot, to be honest. Some of the bigger projects, I can have 1,000. It's not that uncommon either. But of course, you need to start splitting it up, because running them takes a lot of time. And then again, short cycle time, it means that executing the tests needs to be very quick, and you don't want to spend a lot of time waiting for the tests to execute, and you don't want to spend a lot of time writing the tests. The writing of the test should be quick. So yeah, importantly here also is that testing is not a separate activity from development. So if we look at traditional unit testing, you might think of testing as something that's going to prove that the system works according to some specification. But test-driven development style of unit testing, I like the term developer tests better because it actually explains a bit more about what it's about. Because test-driven development style testing is more about guiding the design process. And in the process, we end up with the test scaffolding, the test suite, which actually tests that the system works according to the specification. So we get this executable specification as a byproduct, but the main purpose is really to guide the development and design. So yeah, just a quick slide on why we should bother with this then. I already mentioned that this improves the design, and fundamentally I think this is more or less because when you write the test first, you are forced to write testable code. Else your life will become very difficult, and you will make your life more difficult than it is, at least not on purpose. So yeah, you tend to get testable code, and then again, what is testable code? Testable code is something that's modular, that's cohesive, that has that does only one thing, and has a clear API, and all these kind of nice buzzwords that we might based upon the principles about how we should develop code. So I think, yeah, it kind of falls out of this testability as a byproduct, really. Of course, we get self-testing code, we get a specification which we can execute, and this is tremendously valuable, as we can always just in a matter of seconds or minutes then just verify that our code still works. And after making a change, we can verify that it still works. And this is a key here, that it really enables refactoring, because at least I'm quite careful to do any bigger refactoring unless I have the test scaffolding in there. If it's a legacy code base without unit tests, this might maybe time to add the tests to it, but it will be more difficult to add tests after the thought than doing it while developing. And eventually this leads to less stress, because if you have a test suite which you can trust, then making a release is quite calm. Actually, it's not something that you lay awake at night about. And the final point I want to make is that when you write a test in this style, it actually specifies or shows how the code is supposed to be called and how it's supposed not to be called. So for a developer, this is a very good level of documentation, because it really shows how the API of the code you are about to develop is going to be used. Okay, so now that we have agreed that testing and testing development is a good idea, let's talk about mocks, which is now the main topic of this presentation. So a mock, in the terminology of Metsaros, it's really a specific type of test double. A test double is something that you use in place of an actual dependency during testing. And it should be obvious why you want to use test doubles instead of actual dependencies. Well, for one, you wouldn't really like your tests to interact with the real world. You would like them to run in isolation. If you have some physical system that actually does something, you don't want it to go haywire during the test. And yeah, of course, it's also much quicker to use a slim mock or test double instead of a real dependency during the testing. It makes the tests run much faster, which, going back to previous slides, is very important when working this kind of workflow. So a mock then is a special kind of test double. It implements behavior verification. So that means that the mock itself can check whether a test passes or not according to some expectations, which you then of course need to specify. And we'll get back to that in a bit, and how we can specify the pass-fail conditions of our test. at least in the context of LMock, the mocks also enables control of the return value. So when you call an API method, you can specify what it should return. So I mean, when you call a stubbed out or a mocked dependency, you can define what it is to return during the test. And yeah, I mentioned already this is a toolkit. It's been live on VIPM for a bit now. I don't think many people know about it, but it works pretty well. At least I've been using it for a year or so, and been very happy with it. It's completely open source. It's free. Just go do what you want with it if you're interested. I have a link on the last slide, but if someone feels like putting in the chat, feel free. What it does, what this toolkit now does, it scripts the boilerplate code, so you can pretty easily write a mock yourself. It's basically just something implementing an interface which basically checks what's queues up the calls to the interface and checks them against some expectations. But using a toolkit like this, you save the time writing the boilerplate, and for the second, maybe more important piece of it is that you get consistency, and you get and the mocks always work the same way. If you write them by hand, they tend to diverge, and you tend to come up with better ways as you write more of them or get lazy. And I already mentioned the API. I think it's very important that the API is readable and that it actually expresses what we're about to test. And here I've drawn a lot of inspiration from what other mocking toolkits look like. For example, GLA, which I mentioned, which is one of the other mocking toolkits out there in the world. It allows for mocking any LabVIEW interface. So you can't mock classes, but you can mock any interface in LabVIEW. So yeah, I'm going to show you in a bit how that's done then. And let's try to give a bit of background to why you would need something like a mock or a test double. And if we talk about software testing, there is a few different approaches, and roughly you can say that we can do direct verification. That means that we can verify the output of a function or VI in LabVIEW given some input data. So this is what we would have in a functional type of module that we're testing, or software system we are testing. So something that always returns the same values for a given set of inputs. Of course, these are very nice. You should probably make as much as possible of the code base functional in a functional style, because it's much easier to reason about, it's easier to test, it runs well in parallel environments and so on. But of course, this is not always possible. But for things that functions, now I mean in the functional way, like in functional programming, always having the same outputs for a given input. Algorithms is probably a good place to use direct verification if you can come up with some inputs, outputs that you want to test for. Calculations, parsing is typically something that's good to test using the direct verification. But then we have all the rest, which we tend to run into. So we want to, and now I grouped it under verifying interactions. And by that I mean interactions with other code modules or with other pieces of our system. So how can we now make sure that the system we are testing makes the proper calls to external code, that it interacts with the hardware, that it behaves in a certain way given some preconditions? So yeah, we're going to look at some examples of what I mean if this is too abstract still. And yeah, before we go to that, let's just look at a few examples of what direct verification could look like. So this is now in LUnit. The syntax should be pretty readable here. The block here on the top right is just a assertion which checks that the boolean here is true. And the test would pass if it is true. So this is a test which parses a string and returns a boolean if it's a passing string. So this would be a typical workflow. We want to create a parser. We first specify a valid response, make that one pass. Maybe we parse the OK out of this one. Then we add a test for a failing case until we have coverage for all the tests or the cases that they're interested in. And this is easy to do in a direct verification type of way. We could also have something like well, it's a calculation we convert from Fahrenheit to Celsius. But let's look at those more interesting cases where we have some behavior we want to test. So I think this is best explained by looking at an example. And here I have now imagined that we have some kind of test system we are working with. It has some degree of sophistication. So we have a few different devices in the system. We might have a power supply, but we might as well have 3 of them in the same system. We might also have some switches or relays that connects the power supply to different nets on the device under test. So now I want to start developing some kind of high-level code which I would actually use, because I wouldn't like to call this from, say, test stand or from a higher level with an API saying turn on PSU 1 or to even worse, turn on the PSU with this IP address and connect the relay by turning on digital channel so and so on port so and so. So instead, I want to wrap this in some kind of higher level driver, higher level module, which I am then going to use when I actually write the test code. So typical basic software engineering, software design 101, really. But what I'm about to discuss now is how can we test this? So how can we now write a test that says that when I call my API, I imagine, again, going back to test-driven development, I will start with defining the API because I need to write my test, so I need to come up with what the API is going to look like. The block diagram would typically be empty here at this stage already. But now I want to test that when I connect a voltage or when I turn on the power to the device under test to the dot, I want to check that the relay is closed, that the power supply is actually connected to the dot. So how can I test for this? There isn't really anything I can directly verify. I could potentially extract some kind of state, which I then would need to wire out to some kind of driver, but then that piece of the code would remain untested. So preferably, we would like to make sure that this actually makes the proper driver call. And this is what we are going to use mocks for now. So So what we will test next is that when I apply this voltage, then I want to make sure that a digital output channel has been set. So what I need to do now is I need to declare an interface for my digital output. And this I will need to do in order to write the test. At this point, we don't really need to think about anything else than that. Let's just focus on writing the test first. So I declare an interface, and I only need to write this one test. So I only add the one method that I really need here. I need a method which sets a digital output channel. And this could now be a compact DAC, or it could be some PXI card, it could be an Arduino, it could be whatever you want really on the hardware side below this interface in the actual production system. But during the testing, we don't really care about the hardware. We only care that the proper driver call has been set called, and then we just trust that the driver will do its job later. This is dynamic dispatch. Someone asked in the chat if this is a dynamic dispatch or static. It's dynamic dispatch, and we're going to override this later with the actual driver. So typically, we would have this is more or less a wrapper around a DAC MX call here. You can probably recognize the port line as state on the inputs to DAC MX. So I know where I want to get with it later, but for the test, I only want to have something that I can work with. Why interfaces are not classes? It is actually a philosophical discussion on why these interfaces. The main reason is that interfaces are composable. You can have a class inherit multiple interfaces. So you can have a DAC, a multifunctional DAC, implementing a digital output interface, a digital input interface, analog input output, and so on. And you don't need to upfront come up with all the capabilities. So it's much more flexible. It's better in most ways. So if you don't really need the private data, go with interface. LMock only works with interfaces as well. Sorry, this is going to be a long rant if I'm going to lay out all the reasons. Good. So, sorry, I need to keep up with the pace here. I reckon I already spent 20 minutes. So what we need to do now is use something called dependency injection. So we need to tell our the driver or the composite PSU, the software we are developing, what the dependency is. And I typically do this using the constructor for required dependencies. So now this is a required dependency of the PSU class, and I feed the dependency through the constructor here, and this is then the abstract interface I feed in. And this is really powerful because now when we write the test, we can feed in our mock to the test. So this is a mock I have generated from this digital output class, interface, and now I can use this during my test, but we still haven't really answered the question, what am I about to compare here? And now we need to start talking about the API and about declaring expectations. So now I want to say that I expect my digital output channel so-and-so to be called with a true Boolean here. So this actually looks a bit interesting in LMock, and it might take a bit of time getting used to the API, but once you get hang of it, this is very readable and very expressive. But it turns the data flow a bit on its head here. So what I do here is I create the mock, and then I say that I expect the one here is something called an expectation. So the second block from the left. It says that I expect one of the following VIs to be called with the polymorphic selector there says that with these same inputs. So I expect this to happen during my test. I expect this mock to be called with the set digital output VI, and I expect it to have these set inputs. And then we have the block to the far right here, which is a verification method, also part of the API. And this now verifies that this actually happened during our test. So when I run this, it will check that this call was made, and it will only pass if this call was made with these inputs. So I hope this was clear now. But yeah, using standard terminology, we arrange something, we act on it, calling the set power to the device on the test, and then we assert that something has happened. And LMock actually produces pretty readable English language failure messages here. So here we haven't implemented anything yet. So then our test will tell us that set the digital output VI expected once, but never called with the expected inputs. I'm just gonna should the output of the PSU go into the test? No, it doesn't need to go into the assertion VI. So here we are not checking the PSR. What we're verifying is the mock. I mentioned earlier that the mocks implement the behavior verification. So we are really verifying the mock, and it's by reference here. So that's why we can just fork the VI. But behind the scenes, it's really a queue which enqueues all the calls to the mock that has been made, and then we just verify that the proper calls have been made. So the question was, do you need to fire the PSU into the verification method? But no. Yeah, I should have made that clear. It's by reference, and yeah, behind the scenes, it's a queue that queues up all the calls and just verifies all the calls against the expectations. So how can we create a mock? Now I had a mock already created here, but to create one, you install the toolkit and you just right-click on any interface and select mock. Then you will end up with a class, and the class will now have a constructor, this create method, and then it will have all the dynamic dispatch overrides, which are now implemented with the logic for enqueuing the calls and so on. And then we have this special when set digital output. So for each API VI or each dynamic dispatch VI, we get one additional method here called when set digital output in this case. And this we're going to look at later, but this is used to declare what happens when we call this set digital output. And yeah, I might later decide that I also need to add more dynamic dispatch VIs to my interface. And if I do so, then my classes will be broken, of course, because I need to override those, or I change the connect pane or something like that, which breaks the implementation. And there is a feature to just right-click then the mock and select update mock from the right-click menu. This will basically regenerate the mock for you and relink it to the new mock, so you don't need to do it manually. Okay, so this is all good. Now we have been able to verify that the relay has been closed where we call this VI here. But we might have even some more sophistication to the system. Now let's consider it that we have something like an interlock here. So it might be dangerous. We might need to make sure that everything has been closed properly, that everything is safe. So we might have something like an interlock, which we need to check that the system is in a safe state before we turn on any power. So now we have an additional specification or requirement here. We need to check that the interlock is safe before we turn on the relay. And if it's unsafe, we are not allowed to turn on the relay. Could you show what the generated block? Yeah, I'll get, sorry, yeah. I will actually, if I only have time at the end of the presentation, I'll look at some real code here with you and walk through an example. So we'll get back to that in a bit. And I'll also walk through the API in a bit. Yeah, I'll try to get back to the chat after the presentation as I'm a bit distracted. But feel free to enter stuff in the chat and we'll get back to that later. All right. Yeah, I was saying that we need to check that the interlock is safe, and if it's safe, we are allowed to turn on the relay. So now we need to write a test for that as well. And now the question is, how can we do that? How are we gonna verify this? And again, we can use mocks to test this. And what we need to do now is, again, declare the interface, because we really need to mock out the interlock. We need to simulate that it's either safe or unsafe for our tests. So we create a new interface, and we then have a VI, a dynamic dispatch here, returning the state of the interlock, and the state could then be safe or unsafe. And similar to before, we need to feed this new interface or the implementation of it to our constructor here, so that the class here knows what to use for the dependency, where to make the calls. And now we need to start writing tests using our new mock. And now this would look like this, and I will walk this through bit by bit here. So the higher row here, or the first row there, is actually pretty similar to what we had before, except that now the expectation here says never. It doesn't say one anymore. Earlier it said that we expect one call to this VI. Now it says that we are never supposed to get a call to this VI with these inputs during this test. Right. So this is a way to declare that this is not allowed to happen, and if it happens, the test will fail. Now, the one here on the bottom, this is the when VI I alluded to earlier. And this, again, is a bit of a mind bender, because I have done something quite unorthodox and put the inputs to the right of the VI. And this is because this is a special type of VI. It declares what the mock is gonna return when it's called. And this also queues up the responses, so you can have call this when VI several times and have it return different values each time. And it also stays on the last value it's returned. So if you have set one thing and call it many times after, it will always return the same thing you set. So this should be read really as when the interlock is called, it's going to return the unsafe. So that's why it's to the right. And the terminals are also on the same places on the connector panes as the actual indicators would be when it's called. So the connector pane is similar to this get state VI, except that what was on the real get state, what was a indicator, is now a control. Hope this was clear. So yeah, let's have a look at the API now before going further. So we have a few API methods. We already saw the two first ones here. So these are all used for declaring expectations and verifying them. These are found on the palette and of course through a quick drop once you have installed the toolkit. And the first one is never. It says that I expect this never to happen. The second one is one. I expect this to happen one and only one time. But I could have one or more. So this means that I expect this to happen one time, but it's also allowed for it to happen more than one time. And then I can have these more restrictive ones on the bottom row here. So we can have, I expect this to happen exactly n times. So for example, I expect this call to be made exactly 3 times. And then the other one here, at least. It's probably self-explanatory what at least means. And I alluded to this polymorphic selector, which we have here in the bottom. So using this, we can select how we make the comparison. So when we check whether this has been called or not, we can decide to have the same inputs. So this means that we match if the inputs to the VI are the same, which we had here. So this will only pass if we feed, or this will only consider it being a match if the port 0, line 3, and state true has been fed into it. But I could also use, so I had same inputs, I could also have any inputs. This is basically that we ignore the data coming into the VI when it's called, and as long as the right VI is called, it's considered a match. At least with tolerant numeric here. So tolerant numeric means that we have some kind of numeric tolerance which we can specify them. So for example, this VI can be called with 24 plus minus something. And the last one here is that we can use, yes, the tolerant numeric. This one applies to any numeric input to the VI then. So if we use tolerant, it applies to all numeric inputs. If we have string inputs, we can use the match string matcher here, and this will pass if the given string matches the input to the VI. And yeah, the web API we already looked at. So basically, when we generate a mock, we always receive a when we API method for each dynamic dispatch. And as I mentioned, it has all indicators replaced with controls, and we can then specify what the mock will return when it is called. Hope this was clear. So yeah, let's have a brief look at what we ended up with here. So it might seem like we spent a lot of time creating a lot of small classes and interfaces here just to write something like a power supply abstraction. But I would argue that this is actually a good thing, and I would personally at least have a lot of small classes that are cohesive and does only one thing over having a few master classes that does everything. So what we ended up with here during this small example was the 2 interfaces, and these are now abstract. And then we had this composite power supply unit which calls into these interfaces. But important here is that it doesn't know anything about how these are implemented, so it doesn't know anything about the hardware we have here. These just implement the interfaces we defined. And this creates a very nice kind of boundary here between the abstractions, the high-level API, and the low-level drivers. And this is what I used to call an architectural boundary. And these are the kind of sieves that we want to get into the system, where we can have these dependencies point in only one direction across them. And this allows for hooking on anything basically on the boundaries, and we can swap out any modules below the boundaries without changing any other module. Of course, changing the abstractions will cause all the callers, the implementers to need to be updated. But the structures should by design be much more stable than the low-level details. So yeah, I won't spend time on this one, just some buzzwords of why this was a good idea and why this was a good thing to go through. Yeah, I have a few minutes left, and I actually would like to show some code. So I'm gonna put this slide up after we are done and take some questions if there are still any there. But just if anyone wants to have a look at the documentation and get the toolkit, it's available on that address here. You can just take a picture of this QR code to access it. And if you like it, please consider giving it a star. This is just for myself to know that someone else finds it useful as well. And feel free to make suggestions and contribute. As I mentioned, it's open source, and I'm happy to have other people participate. So let's have a brief look at some actual code. So this is actually the shipping example with LMock, and it's supposed to illustrate a workflow where we are about to develop a driver. So a driver would be something that's typically considered difficult to test, and here we can now really use Box to make the testing easier. The example is quite simple, but I hope it shows the point I'm trying to make here. So I'll take you through the workflow here in 7 minutes, and let's see if we can understand what this is about. So on the tests here. Sorry. Yeah, thanks. Now I actually need to change. How can I change from the presentation? Stop sharing. Share screen. Okay, now we go. Entire screen. Yeah, that would have been silly if I would have made a demo without anything visible. Now this is pretty small. Let's just make it a bit bigger here. Scale. Yeah, you need a huge screen when working in LabVIEW. At least I need one. Or working with documents or whatever. Yeah, so let's have a quick look here. The scenario I'm considering here is that I have some kind of instrument talking over a serial interface. So it's basically something that uses NIVs in the lower levels to communicate with an instrument. And I start by declaring a test case here. As I mentioned, we write the test first. And now I start with this first test, and I want to check that when I read the instrument. Sorry, is it still too high resolution? Or
yeah, it does look like it's so.
Sorry about that. Is it any better? I don't know if this does anything to the share. I'll just try to share again because my screen is changing, but nothing is happening to that. Over conversation. Yes, I know. So did it get any better? No, sorry. I think I actually changed the wrong screen. Sorry. Let's.
Now it's better. Yeah, definitely.
Okay. Sorry about that. Yeah. Okay. Well, what was I? Yeah, the first test I'm about to write. I want to check that the correct command is set on read voltage, and let's see what this might look like. So I have a test case here, and now this is the API you should use all earlier. And sorry, here I have my driver, which I have created an API for. I have a create, I have a read voltage VI, which I'm calling here, and then I destroy these are that at this point they are only empty. I would just create the APIs that I have something to test against. And then I need to check that the serial port has been called with the proper message here. And this now could be something that I get from a manual. I might not have the instrument yet, or I could just play with the instrument on the bench and send some serial data to it to check that how it behaves. But now I can then define how my driver for this instrument should behave. And really, for making something as simple as this, it might be a bit overkill, but you rarely do anything that's only this simple. It always grows and gets more complicated. And at that point, it's always a good thing to have this test scaffolding. So this test should now be read as expect one call to this write serial VI with this input. And now this input is exactly the same. So let's look at what we had here, what I needed to create to build this test. So I needed to create this driver class, which is over here. It has create, read, voltage, destroy. These are the 3 VIs I have dropped here in the test. I needed to create an abstraction for my serial. And this should be pretty familiar if you've ever seen NI Visa before. This is basically just a wrapper around Visa because I know I will use it later. But during the testing, I don't want to send anything on any real serial port. I just want to make sure that I call the driver with the correct inputs and that I can parse the outputs coming from it. So yeah, this test should be pretty clear now. We can run it and it first fails, then we implement something that makes it pass. And I won't even bother with looking at the implementation because it should be pretty straightforward. And this is actually a good thing that we incrementally add tests, and the implementation is one at a time. It's straightforward, but it accumulates and builds up to the bigger system. So let's look at the second test here that I have. So the second test is that I want to parse the response when measuring voltage. So now I know what the instrument is responding with, and I want to make sure that I parse it and return a proper numeric value from it. So now I'm going to use the when VI, which I got from the mock. Yeah, I generated the mock. I forgot to mention that already earlier. And I have the 2 API methods, read and write. And then I have a when read and a when write. And now I use the when read method to specify what the instrument is returning. So this is basically simulating a response from the instrument here. And I could also simulate an error, for example, and this might be useful to check to handle connection losses and stuff like that. You could set up error handling conditions if that's of interest. And yeah, now this test just tests that when the instrument returns this value, I want to make sure that my driver actually returns a numeric with the same numeric value. Basically just testing the parsing here. And finally, I have added one more test just to check that it also works for negative values. And this is very similar to the earlier one. So yeah, this example is walked through in the documentation or also that I linked to in the presentation. And what I did at this point when I had written this was I thought that this would be a very nice place to just demonstrate how to use the decorator pattern. So I decided to add a logging decorator to this one. And this is just to highlight the siege that we get with these architectural boundaries and how easy it is to add functionality without changing what we have already here. So the next thing I did was create this serial logging decorator. So a decorator is really a class. Jesper asked if I could end up with float precisions, issues with float precisions on this test. Probably. What I typically do is I only care that it's within some tolerance the same. So I could add a tolerance to this here. But really, when you run this test, if it fails, then you're going to get the message explaining why it failed, and then it will be pretty clear to you why it failed, and then you can handle it case by case. But I rarely think about it up front. So going back to my idea of using a decorator pattern now so the idea is that I might be interested in seeing what my system is doing as it does it. So I might be interested in seeing what goes on the serial bus here. And this can be done very nicely by using the decorator pattern. And the decorator pattern is something that basically is a wrapper for a class. So we have an interface, then we have a class implementing the interface, and then we can create a decorator which implements the same interface. It wraps the class, the concrete class, and every call to the interface is forwarded to the class, but we can add behavior on top of it. So if you're familiar with the pattern, this should be understandable what I'm trying to do here now. So the idea is that we can we start developing the decorator here with a test case first. So we check that serial write data is written to a log, and now I needed to define what a log is. So I made an interface for that as well. And I have a VI which is called write to log. So this is a simple VI which takes a string input and writes it to some kind of log. At this point, I really don't care where this ends up. I can direct it wherever I want when I actually use it later then. So here, again, another example of a test using a mock. We create a mock log this time. I have created a mock for this log interface. I call it with the one method, and here I wanted to show that we can use the match string comparator here. So we select, we say that we want this to be written to the log with this text, but since I use the match string comparator here, it means that this will pass as long, even if I add a timestamp to it or add some other context to it when it's written. And here, this is a special kind of constructor. So this is basically something that attaches the decorator to a class. So here we have a serial coming in, and we have a decorated serial coming out. So this is called serial with logging. And here I have the log destination coming in. If you're unfamiliar with the pattern, just this is what it looks like. So we have the serial decorator being this class I have here. This is what I'm developing, this is what I'm testing. And the wrappee is the serial interface, and the log destination is now the log interface. So I can run this test and see that it passes. I'm running out of time, so I will not go through all these, but no, the decorator is not controlling any hardware. The decorator is just something that wraps this call. Let's see how it's implemented. So basically what it does is when I call, the decorator implements the same interface here. When I call the write on the decorator, it calls the same write on the actual class here, and it sends a message to the log. So it basically adds behavior to my class. So I can, without changing my driver here, I can add logging to it by decorating it. So I add something on top of it without changing the implementation. This is the whole idea here, that we can now have small classes. The decorator is only concerned with logging what I send to the interface, and the Visa driver, the low-level driver here, is the implementation of the serial interface. That is, this is only concerned with wrapping the Visa. So we have very good separation of concern. All the classes are small, they do only one thing, and then we compose them. And this is what I wanted to show, the last thing before I finish here, how we now compose this then into where we use it, and what our software starts looking like when we write software in this way. And we had now a few, I think it's like 4 or 5 different classes, a few interfaces and so on. And when we write an application, we tend to get more setup code here. So building the objects it's very declarative. There's not a lot of logic here. We just connect the dependencies together. So here we have something simulating a serial port, which we now add a logging decorator to. The logging decorator here I have implemented. This is a simple implementation of this log interface, just forwarding the text to an indicator. And the indicator is then fed by reference into this logger. Then I feed this into my driver. This was what I started developing, the driver here, which now takes a serial interface, but I use the decorated serial interface. And this is now to show how we can use the CEBID architecture here to add logging without changing this driver. So this driver doesn't know that it's being logged. It doesn't know that the logging decorator is there in between. It just cares about interfacing with the hardware. Again, separation of concerns. And we can run this. And when we measure, you see that we get the measurements here in the front panel control without this driver or knowing anything about it. It only cares about reading and writing from the serial port. So yeah, I think I'm running out of time here. Sorry for rushing here. I spent more time than I thought on the first few slides there. I have a question here from Virant that so the mock tests the logging capabilities only. The mock verifies the test. So just to get the terminology, we have the serial logging decorator test. This test tests the behavior of the decorator. This test tests the behavior of the driver, this one. So we have this test tests basically this class. We have the serial logging decorator test testing this class. And then when we use them, we don't care about the tests anymore. Then we just use them in the demo here, which would then be representing the application. And we have a few concrete classes. I had these two, which I didn't actually show. They are very straightforward. They are just implementations of these two interfaces, so that I have something to use in my demo. The simulated is just something that gives back a simulated random reply. And this write to log is basically just something that directs the log content to a indicator. So yeah, with that, I think we can just quickly put up this slide again. And if you have any further questions, I'm happy to stay around and talk. I hope this was somewhat clear. As I mentioned, the API is a bit unorthodox, declaring expectation and also the when API, but once you get hold of it, it enables very expressive tests and they become very easy to read. Also, the performance of this is very high. The tests, the LMock internals are basically just queues in LabVIEW. And as you know, queues are very, very fast data types or data communication mechanism. So running the tests is very, very fast compared to, well, many other things. Thanks, Kival. Good to hear that you liked it. Verat says that he kind of gets it, but that he's also sleep deprived. I can imagine it's been a long night, or maybe day for you. I don't know. Snake. Good. Someone has seen the YouTube video. Yeah, I have a YouTube video where I made a snake game using test-driven development. Could probably come up with something similar for mocking. That could be fun if I just find the time. And also, if you have questions regarding how this works or how it's supposed to be used or something like that, just let me know, and we can discuss it out and maybe also add some more examples to the toolkit. I think it requires a bit documentation, a bit of example code to understand or to really make it easy to learn. Yeah, I didn't mention it, but LMock, it's basically a plugin to or an add-on to LUnit. So as it's written now, it requires you to use LUnit, but if you use Karaya, I guess it could be ported because it's not really anything else than the verification method that's specific to LUnit. So if someone is really allergic to LUnit and want to use Karaya or via test or something else, it could probably be ported, and I'd be happy to include that in the toolkit as well. There's really no reason not to, other than I haven't really had the motivation to do it myself. Any cases where Karaya fails but LUnit does it? I'm not sure I get that question really. So I mean, both are basically just comparing stuff, and if a true value is true, then both should pass. What Karaya and LUnit does, it basically just runs the tests and compares the results, generates a report, shows a UI, stuff like that. But I mean, the test apart from the efficiency LUnit has, there is not much difference. The efficiency, I mean, LUnit it's fast. Then we have the project integration. At least for me, the workflow, being able to run a single test case from the project explorer is a big one, and having the overlays when the tests pass or fail. But really, no. I mean, you could use any toolkit you prefer. It's more about workflow than anything else. I tend to like to group by tests in classes and then being able to selectively run them. But if you're allergic to that and prefer to do it in other ways, feel free. It's really just a question of preference. Right. Yeah, I think we're reaching the end of the hour. But as I said, just hit me up, send me a mail, LinkedIn, or in here in this what is called Ring Central on this platform. I'm happy to continue the conversation. So yeah, if no one has something else to add, let's wrap this one up and go see what's else on the stages. Thank you very much for the discussion and for participating. Cheers. Bye.